Hello everyone, my name is Mohammed Saeed Khoory, and in this presentation I'll be talking about the development of the camera interface board used in the Emirates Lunar Rover. So before I start, I'll give a brief overview of our mission. The Emirates Lunar mission is the UAE's first lunar and rover mission, and we've built our rover using it's a small rover, low cost, manually driven, 12 kilograms in size, and it's designed from scratch by the team. We use a lot of the commercial off-the-shelf parts as well as our own custom design. And we have a picture here of the FM rover as well as the engineering model. This is delivered to the moon using the iSpace M1 lander. iSpace is a Japanese commercial company, startup. There's a picture of the lander from iSpace. We actually launched just 2 days ago in December 11, so that's exciting. And this is a technology demonstration as well as a science mission. So we have another picture here of the rover, and this is when we did our testing in the UAE desert in Dubai. You can see here we have the mast completely deployed. We actually have 3 visible cameras, including 1 microscope. You can see one of them being on the mast, and the microscope is down here. And there's one in the back being a redundant camera. We have a thermal camera, as well as a Langmuir probe. Langmuir probe is used to sense the plasma on the moon. We have a material adhesion experiment where we have different materials stuck on the wheels. You can see some of them here, although they're covered by Kapton tape. And then we look at the way it interacts with the regolith on the moon and using the cameras. We also have a deployable mast, as I mentioned. You can see that here, and the 2-axis gimbal for the primary camera. We have two communication systems, one through the lander and one direct to Earth. The direct to Earth one is redundant and like a backup. This was originally meant to launch in 2021. The mission is actually quite, it's meant to be low cost, and we also had a really tight schedule as we started only a few years before that. So it's a tiny team, a tiny schedule, and a tight budget. That was development was quite tough. And speaking of the team, the ELM team is we were the Space Robotics Lab at MBRSC. We started as a small R&T team consisting of only 3 people, and then we grew to around 10 to 14 people. You can see the team here in the Kness facilities in France doing the final thermal vacuum test on the FM rover. 4 of these people are software engineers, and 2 of them, including myself, are dedicated to onboard software. Santosh Amilineni is dedicated to developing the software for the CIB. You can see his picture here. Many of us were fresh graduates when we first started. See here, Sultan, for example, was a fresh graduate, Salim, Amna. But many of us also had previous experience with satellites, such as myself. I worked on the Emirates Mars mission and Khalifasat. And Ahmed Salim here has even more experience with Dubysat 2 and Dubysat 1. However, space robotics was a completely new field for all of us. So we were starting fresh and quite exciting, but also very difficult and lots of challenges ahead. It's a small agile team, so as we were learning, we might change the design. Things change very quickly in the mission, in the project, and that's just a characteristic of our team. So initially, when we first started, we planned to use a commercial off-the-shelf industrial grade ARM Cortex A8 IMX6 board. That's a dual core board. We also intended to use just typical smartphone class cameras. They're easy to use with these kind of boards. Very straightforward. The video encoding is all handled easily. There are already Linux drivers that we can use. However, it's not really great for science. We can't really control the encoding process. We can't really get the raw pixels, that kind of thing. And also we had to go through qualification. Also, we would use an SD card for storage, which is quite easy. We can just simply write to the file system. And this is how we first started. We used one of these boards. This is a IMX6 board from NXP. We would use Yocto Linux, which is a meta distribution, where we can make our own distribution for the board. But then later we decided we would want, a more scientific mission. We want to have more science involved. So we wanted to get better cameras, and in a collaboration with Kines in France, we were provided Caspex cameras, courtesy of Kines. And these are space-grade 3D plus sensor cameras, which use space wire, and as a result, we couldn't really use them with this kind of board. We needed a more reliable, more space-worthy solution to continue with the IMX6. So we needed some kind of redundancy because this is not really meant for space. And we also needed a custom core to handle space wire because nobody uses space wire except space grade boards, right? So we decided to make our own board with IMX6 initially, and we had like dual redundant IMX6 SoCs on there. And we were running at 5,000 DMIPS at 800 megahertz, and we have a dual core SoC. We had a custom FPGA with the SpaceWire core in it, so that one of these two can access the SpaceWire interfaces. We have 3 interfaces here for each camera. It was a really complex board. It was densely packed. We even had a daughter board, which it's not pictured here, and we figured this is not really a good solution. We've had a lot of trouble working with it, and we needed a better solution. So we reached out to AEC ClydeSpace to look at their GR740 based design. And we have this board here provided by AEC ClydeSpace. This is a GR740 Leon 4 FT based system, and it's customized to fit our Rover. And it's running a quad-core Leon 4 FT at 250 megahertz. When compared to the IMX6 was around 5,000 DMIPS, whereas this one is 1,840, which is quite lower, but we figured we could do something with it. We have 512 of SD RAM and 16 megabits of MRAM and 256 megabits of SPI flash. And the RAM in particular was quite comparable to the IMX6, so this was good for us. We have 4 SpaceWire interfaces, 3 of which were used for cameras, and we also had GR CAN cores, which allowed us to communicate with the rest of the rover and the ground system. However, it doesn't have mass memory, so we only have MRAM, which is used for the bootloader, and the SPI flash, which is really used for the Linux image. So we we used ClydeSpace's TCM board for the mass memory, and this is a ready-made board. It already has its own custom software built in. We used it like a black box, so we didn't really need to customize too much. And this was connected to the main camera interface board using SpaceWire, and that provided 32 gigabytes, which we use for images, video, previews, kind of thing. We have continuous partitions in which we store all of these images, whereas partition 0 was a random access partition, and we can store a file list of what has been stored into the other partitions, as well as new versions of the ISW. The imaging software, on the other hand, is the software that actually controls all the cameras and does all the logic and receives the commands from the ground system, and also the OBC, the main OBC on the rover. And this is a Linux-based executable based on C. It is also able to spawn additional Linux processes, so we would take advantage of the Linux userland, like we would use GStreamer, shell commands, XZ, that kind of thing. We accept commands from the ground system or from the OBC, and this is thanks to CSP that makes it easy. We use TempFS for images when we first capture them from the cameras, and then we store them into the TCM using a command. We use the CubeSat Space Protocol, which is an open source protocol which you can find online, and this is used for communication with other subsystems on the rover, especially the onboard computer, as well as the ground system. We also have a custom file transfer protocol made for the mission, and the same C code that we use on the OBC, which is running FreeRTOS on a Cortex M3, can also be used for the GR740, which is running Linux, which is quite nice. Um, so part of the transition to the GR740 based board was the fact that originally we used Yocto Linux. Yocto is a meta distribution, and we didn't want to rewrite our ISW because we've initially based it on our IMX6. And in order to prevent a complete rewrite, we decided to use GR Linux instead of the usual RTOS, which is typically used on the GR740. That is based on build root. And as a result of this, we moved our code very quickly to GR Linux. It took us about maybe 4 days, maybe less. That was nice. And all of our code was using socketcan, and that also made things very easy because we didn't have it to write a lot of CAN code as a result. Also, our GStreamer code was also ported, so all the video encoding stuff, all the image compression, that kind of thing, debayering, all of that, we could just reuse all of that. That was good. So we also, in order to start our development, because the board wasn't ready initially, there was a lead time on that. We got a GR740 development kit in order to start our development. Then we would transfer the code to the CIB after it has become available. However, there are some key differences. The performance is much higher on this GR740. The memory layout is quite different as well. So we would simply just use different build configurations for each target and make note of the differences when we develop. We did face quite a few difficulties, and I think it's important to mention those, just to maybe see everyone's opinions. So one thing, if you may have noticed, we have a mass memory board and a main board, and that was connected with the SpaceWire, and this is mainly because we didn't have any mass memory on the main board, and that kind of configuration really increases complexity. We could not mount the TCM like a normal file system as we did before with the IMX6, so we had to write really custom software to handle the storage. Also, the TCM has these things called continuous partitions, which we had to use for images, and that wasn't quite as straightforward to use as a normal file system. So that made things a bit complex. We had to rewrite a lot of that. Another difficulty we faced is the booting process. So typically on these boards, people would use an RTOS, and their image would probably be like 1 megabyte or maybe even less, or that isn't much. However, with Linux, our Linux image, we brought it down to about maybe 6 megabytes, which doesn't sound like a lot, but it is quite a lot, and we couldn't fit it into the MRAM. So we had to use a bootloader from Geisler to boot the image from the SPI flash. The boot time is 2 minutes, which is acceptable because it's not the main OBC, but it's a little long. Ideally, we would have it in a few seconds, but that's fine. However, the main issue is that updating the Linux image in the SPI flash using German took way too long. It took like 6 hours. So our workaround was to avoid updating the image altogether. We would simply have one image on the Linux image would stay the same all the time, and simply update the executable when we need to. And that would happen on the TCM, and it's not ideal, but this is the way we go. Another possible workaround we haven't looked into too much was to load an executable into the RAM in the Leon 4 and the CIB, then have that executable flash the SPI. But we haven't investigated that too much, but we think it would cut down the storage time significantly. The SpaceWire driver in GR Linux had some limitations we had to work around. RMAP was not supported. We really needed RMAP for that, for using TCM. So we had to implement that in software. Also, the camera was providing longer length spacewire packets that was not supported, so we had to modify the drivers for that. And one thing to note is modifying Linux drivers is really not as straightforward as modifying, RTOS drivers. Linux is a lot more complex, so it's not as easy. Another driver we had to modify was the CAN drivers, because the drivers did not really initialize the necessary GPIOs on the CIB initially, so that also had to be modified. More difficulties. So we were used to using a device tree on the ARM board, but that wasn't available on GR Linux, and that made things a bit confusing at first, but we figured it out eventually. Another thing to note is that Spark is big endian, and if you wrote your code properly, this wouldn't be a problem, but it is very easy to assume that your system is little endian, especially if you're running ARM and you're on a little endian system on your PC. So this can catch you off guard if you're doing that, but it's not a big deal. It's just something to note. It just makes development just a little bit harder. Another problem we had is the power consumption. So despite the fact that our DMIPS is a fifth of the original board's DMIPS, we were using twice as much power when we compare the IMX6 with the new CIB. And it's not much. It's 3 watts, 5 watts, but for our rover, it's a small rover. Our power generation is about 7 to 8 watts, or 6 to 7 watts on average. So, and we do have a battery, so it wasn't a big deal, but it was a bit on the edge, and that was quite a lot for a rover. And the other thing is we didn't really have a lot of power saving modes on the CIB. Things like we S3 sleep, variable clock speeds, putting the suspend, that kind of thing, suspend to RAM. That would be very useful for us, but we didn't have it. Also, the performance was quite low, and initially we wanted to do a video storage, H.264, that kind of thing. That's why we were using an IMX6 in the first place. But we found that the CIB was much slower than the IMX6. We didn't have hardware compression of video or anything like that. And generating a preview of a 4 megapixel image took about 5 to 10 seconds. And when I mean preview, I mean simply converting a raw image to a JPEG, which would take probably less than a second on the IMX6. So that was quite a big difference. However, it wasn't a big deal for us. It was still within acceptable performance requirements, but it's just something to note. We also found that as a result of this, live encoding of video for streaming, which we initially wanted to do, was considered impractical, and we couldn't do it. So some lessons learned from this entire exercise. Live video streaming. So when we first started, we wanted a live video stream from the moon. That would be really nice. We actually thought this was a requirement for controlling our rover. But as time went on, we realized this really isn't a requirement. We could simply make do with taking images, and the latency wouldn't make it very practical anyway. But however, it was feasible with the IMX6 and with the smartphone cameras, but with SpaceWire and the GR740, it made it really difficult. Actually, you might think that our hardware was quite over-specified, but a lot of our hardware requirements was driven by this, and in retrospect, this was a kind of a mistake. If I had to do it all over again, I really would go for a lower power board. Executing shell commands. So we're using Linux on the CIB, and initially when we first started, we decided, executing Linux shell commands is very dangerous from the ground, and I still think this is true. We should not base our commands on the Linux shell. However, it is quite useful in case something went wrong and you really needed to get into the lower levels. So having you could say like an emergency command just for executing custom shell scripts or custom shell commands, that is very powerful, and it's a good thing to have when you're running a Linux system on board. And we found that when we develop code for Linux, we found that it made the user code easy to write, but driver code hard. Um, we depended on a lot of abstractions on the Linux kernel, and this made it really easy to move between the IMX6 and the GR740. We could simply use a lot of open source libraries, programs that just work. You can just execute them, like XZ and GStreamer. However, modifying the kernel drivers is quite difficult as compared to RTOS. So there's a lot of complexity there. So in conclusion, we use the GR740 based CIB for camera control. We use the quad-core processor for compression and image previews, and we also even tried to do live video, but we removed this due to technical difficulties. And transitioning to the GR740 from on our board was successful. However, we did have some difficulties, and Linux helped us a lot with this. And several drivers were not mature enough, so we had to, work on that as well. And as a result, some driver code development was difficult, but the user code was quite easy. And that's something I hope to share. I think you would find useful. Thank you everyone for listening to my presentation. And if you have any questions, you can send it to my email, which was on the first slide. Thank you.